Okay. Morning, everybody. Welcome back to Chem 1. Yesterday, we talked about, not all of you are here yesterday. I hope you watched the recorded version. Yesterday, we talked about a new state function, free energy. And free energy encapsulates a lot of what we need to know in a chemical system. So free energy is what determines the direction a chemical reaction would go. So if you have some chemicals and you want to know if they're going to proceed towards products, the free energy determines what that does. If the sign of the free energy is negative, then that's a spontaneous process. We saw free energy was intimately related to the second law of thermodynamics. That is, the entropy of the universe is always increasing. Every process that happens naturally increases the entropy of the universe. But it's hard to track the entropy of the entire universe. So we found this free energy parameter is just a property of the system. So we can concentrate on the system, yet it's directly related to the entropy of the increasing entropy of the universe. So it allows us to explain things like this. And we can do these chemical reactions here. Let's just, since I'm doing it this way, let's just open the browser. So here, I'm going to show you a chemical reaction. This is annotated. So a filter paper moistened with a little water, and we're going to take a beaker, put it on there. This has thiocyanate, and we're going to just dissolve it in water. Actually, it has barium hydroxide and sodium thiocyanate. And there's a little bit of moisture. We're just going to mix those two things together, both solids. And as that solid form, as that is mixed, you can see a chemical process, a chemical reaction occurring. And that chemical reaction is extremely endothermic. So it's so endothermic that it freezes the board to the beaker. So the question that comes up is, that is an enthalpy change. And the enthalpy change is not sufficient to predict that chemical reaction would go. So if I plot enthalpy for this reaction, it's reactants and products. It doesn't look like a product. One of the a lot of cool things about this board. One of them is it recognizes that you want to erase stuff if you put your palm on it. Handy. Right with your finger, and it draws. So products, reactants up here, products down here. Oops, in this case, it was endothermic. I'm glad the erase is possible. The reactants, products. It goes uphill. There's an absorption. It's endothermic. Positive enthalpy. That would say, in our bigger picture, we were talking about valleys and where things end up on the enthalpy landscape. That is counterintuitive. We said, well, that is against the enthalpy situation. I have to go uphill. Why would I end up there? And why does it spontaneously, without any interaction from anything else, go up that hill? So we found last time that it is the entropy contribution. So there's an enthalpic and entropic contribution to chemical reactions, and the combination decides whether the reaction goes spontaneously. So we defined this thing called the Gibbs free energy, and we defined it as delta G is the enthalpy change in the system minus the absolute temperature times the entropy of the system. We found out standard entropies are relatively small, so they're on the order of joules per Kelvin mole, and enthalpies we've already seen are on the order of kilojoules per mole. So this is a small factor, but it adds a temperature variance to the system, and the balance between those two things determines whether the reaction is spontaneous. In order for a reaction to be spontaneous, we said that the free energy change must be negative, must be less than 0. So you can have this situation where you're on enthalpy hill and you have an endothermic process. You're going up the hill as the reaction proceeds. So the reaction is absorbing energy from the surroundings, but as long as there's also an increase in entropy going uphill, you're going to multiply that by minus T, minus the temperature. So this term is going to tend to make the free energy negative. And if this term is big enough, then you can roll down the free energy hill. And it's the free energy hill that determines the overall spontaneity of the system, whether the reaction goes. And of course, there's combinations. If it's exothermic to start with, that's great because that already makes free energy tend to be negative. And you have to determine if the entropic contribution helps you or hurts you. If the system tends towards lower entropy, then that would be an inhibitor of the system, because going negative delta S and that negative T, temperature in Kelvin is always positive. So you don't have to worry about the temperature changing sign. The temperature is 0 to infinity on the Kelvin scale. So T is always positive. So increasing or decreasing entropy tends to make the free energy positive. So that hinders the reaction. And you can have, of course, all combinations of positive and negative combinations. You can put this little degree sign up here. That little degree sign means you're talking about the standard states. So the free energy difference between all the reactants in their standard state. And remember what that is. It's this crazy situation where everything is 1 molar or 1 atmosphere of pressure. And the products, you're comparing it to products also in their standard states, 1 atmosphere, 1 molar concentration, or the pure liquids and solids. So it's a completely artificial situation, but it tells you the relative free energy between those products and reactants, and is a good predictor of whether that reaction will proceed towards products or from products to reactants by the sign of the standard state free energy. So you can calculate standard free energies. We do have tables of standard state free energies of chemicals. So you can do the usual thermodynamic cycle thing and calculate standard state free energies for arbitrary chemical reactions if you can find the free energies of the products and the reactants in a standard state table. So this brings us to a couple interesting things. One of them is free energy is called free energy for an interesting reason. And we're not going to dwell on it too much, but it helps us understand what's going on. Free energy is the amount of useful work. So the change in free energy is the amount of useful work, the maximum amount of useful work that you can get when a chemical reaction occurs. So we've been talking about enthalpy release. And we're saying, well, you release all this heat that could be used. You release heat. It could An expansion could be used to do work. The heat could be used to boil a system, run a turbine. That release of energy, delta H, it turns out you cannot use all of that. That you can't convert 100% of your enthalpy to useful work. The free energy tells you how much you can release as useful work. And it even, when you think about it that way, it even starts to make a little sense. This delta G that we wrote is the enthalpy of the reaction minus something. This entropic component. This component says you can't use all your enthalpy for doing useful work. So you take away a little. This is what gets taken away. You can kind of think of it in a lot of ways, and we'll do it kind of hand wavy here. This isn't mathematically correct, but if you take a piston, a sample here, and you use a chemical reaction to squeeze that system down so it gets compressed, you did work. You used some of your enthalpy to do work. But if this is an isothermal process that heated up the system and you have to have that heat leave to get back to an isothermal process. Now, what if you wanted to do the cycle? What if you wanted to come back to here, let the system come back so you can do it again? Well, this heat that left the system is kind of lost energy. It represents that lost bit of energy. When that energy leaves the system, you can't use that heat again to expand the gas and do work back. So this heat here, I cannot use again to compress. And the reason we kind of understand, because heat is random motion of the surroundings now. And that random motion we created in the surroundings made what we call entropy. So the entropy of the surroundings increased. And you can't reorganize the particles and make them go in all one direction to squish that cylinder back down. So every time you do this cycle, even if it's perfect, no friction, no nothing, absolutely ideal, you always lose some amount of energy. And that's what you can't reclaim. And this process, that's why this, even in this cyclical process, you can have entropy in the real world of the universe increasing. You come back to the same place, but it doesn't matter. The universe entropy increased. And so that's why you lose this energy. You can't get all your energy and do useful work with it. It has to do with this randomness of the heat and not being able to harness it to squish it back down. You can arrange it, of course, that you can use energy from the surroundings again, but it takes more energy than this amount of heat to get those particles to work together. So no matter what, you lose in this system. So the first law of thermodynamics says energy is conserved. So you can't win. If you go through a cyclic process, delta E is 0. You can't make any energy. The second law of thermodynamics says you can't break even either. So some energy is lost to the disruption, the general entropy of the universe. Okay, so I'll write those words down. So delta G is the maximum useful work you can get from a system. So you can't use all the enthalpy that you get to do useful work. Okay? You may see this in the homework, or we may write that on an exam. What's the useful work you could have got out of that process? That's the same as saying, what is the free energy difference between the products and reactants? Great. So let's look at free energy space. So here's a space where the axes are the entropy difference and the enthalpy difference of the system. So two system parameters, if a process is endothermic, that's positive, that doesn't help you. It's makes the reaction tend to not be spontaneous. And we know most endothermic processes aren't spontaneous. If it absorbs heat, it's not likely to go on its own. That salt dissolution that we saw there is kind of rare. You got to find a reaction that'll do that. But if the system also decreases in entropy, that's a double bad. So the entropy decreasing, and absorbing energy, these two would both, since T is always positive, that negative sign is there, these both would tend to make the free energy positive. So in this region, where the enthalpy change positive, the entropy change negative from the origin here, these reactions are not spontaneous no matter how big you make the temperature, no matter how hot you get it. Since you have this combination of signs, they always inhibit spontaneity. They always tell you that reaction won't go. And you can do all the combinations, of course. If it's exothermic, that helps you. And if it goes to a less ordered system, that is a increase in entropy, then both of those signs tend to make delta G negative. And those processes go at all temperatures. That is, they're spontaneous at all temperatures. And of course, there's the other combinations. If you're exothermic, that helps you, but increasing the order, decreasing the entropy of the system, well, if you have temperatures low enough, then this bad component that's making delta G more positive, if it's small enough, so T is small enough, then that reaction can still proceed just at low temperature. And of course, the other combination, endothermic isn't helping you. That's what we saw with the barium and sodium thiocyanate, those two solids making that liquid, but you went to that liquid and you increased the microstates, you increased the entropy of the system. And if that helps you, then these situations will proceed as long as the temperature is high enough, as long as T is high enough that the entropic term overwhelms the enthalpic term when it's endothermic. So let's do a chem quiz then. What is the enthalpy change, standard state enthalpy change? So again, I'm beating this over the head with you. If I say standard state, it's not the chemical reaction starting with all reactants and no products. It's not the chemical reaction. If I say standard state enthalpy difference between the products and reactants, this has to be here. These are both gases, so I have to have 1 atmosphere of this dimer, N2O4, and 1 atmosphere of pressure of the reactants. I'm comparing those two states. Not the initial state where it's all products, not the final state where it's a mixture, this artificial state. So this is the number you'd get from tables where you take standard state enthalpy, products minus reactants. So delta H for the reaction is shown. This is not shown, but I'm telling you the reaction is spontaneous at room temperature. Can you determine then what the sign of the enthalpy is? Let's talk about that and see what we come up with. I have guests here, so this first time I'll talk to the people here. It's just person, actually, in the studio, and then I'll join a Zoom room for the next one. Okay, let's come back together. If you haven't pushed a button yet, go ahead, take a stab now, and we'll see what you guys are thinking about this. About how many people do we have in the Zoom or? Okay, so we'll see if we can get about 100 responses here. We're getting there very quickly. So let's see what you think. It's quite popular. About half of you think delta H is less than 0, delta H is negative, and the rest mostly are thinking it's positive. Not too many people thought it was 0. Let me tell you what I think, and I do agree with the A's. Why is that? I think I might try something today. Put up some possible arguments for each answer, maybe to stimulate your discussion. So basically, you just have to pick the right argument. That might help you do some things. Here's some arguments for this. We're going to go through them. So we told you it is spontaneous. So the free energy change has to be less than 0. But just by inspection here, you can say there's half the number of particles in the products as opposed to the reactants. So the number of ways you can arrange half the particles is smaller. There are fewer microstates available on this side than this side. That's a decrease in entropy. So delta S is going to be negative, And we can predict that just by inspection. We don't even have to go to a table. We could go to a table of the relative entropies of formation and calculate that, but that is hurting you. That's tending to make that minus T delta S is tending to make that term positive. So in order, I told you it was spontaneous. So in order for it to be spontaneous, this term must not only be negative, it must be bigger than this positive contribution. So that's what we chose, a negative number that's bigger than that positive combination here. Now, the temperature factor is just telling us at which temperature that occurs. I told you it was spontaneous at that temperature, 25 degrees C. You don't know, we had that chart of 4 quadrants. You don't know whether that is a high temperature or a low temperature until you actually have the values of delta H and delta S. Temperature in that 4-quadrant diagram is just the absolute temperature in Kelvin. Sometimes they're high enough, but the question is high enough. You have to get T's high enough or low enough, in this case, for the enthalpic term to overwhelm the entropic term. So in each of those, we consider all temperatures, but they're only spontaneous at high temperatures for that one quadrant, at low relative temperatures for the other, or all temperatures, 0 to infinite K in Kelvin. Okay, so I'm going to boil water here. What's the correct plot of the standard state free energy change versus temperature for this chemical reaction? So I'm going to plot delta G versus temperature. So now you have to tell yourself, here, this is kind of representing those quadrants. I'll give you a hint. Delta G is negative for all of T. That's one of the quadrants. Delta G is negative at low T. Delta G is negative at high T. And you know delta G is a function of temperature. So let's talk about this for a minute and see what you think. Okay, coming back to the group, that was helpful discussion. Oh shoot, I think I was going to show you those arguments. Remind me next time. This will, stimulate, I think, your discussion. So, what are you thinking first? Let's look at what you're thinking. You are thinking that we're absolutely equally tied between B and C, and I think I agree with those situations. Let's try a quick experiment here. Let's vote again. I won't explain it yet. Let's vote again, but let's go back to those arguments for each of them. So you can see here these arguments. Does this help us converge to B or C? Just take a few minutes to read those. Does that convince the B's to go to C or the C's to go to B, the A's to go to B or C, or everybody to go to A? I don't know. Talk about that for a second. Okay, so let's see what you're thinking there after kind of looking at these arguments, see if any of those convince you. We're tending now towards C, and I like that. Fantastic. C is the most popular now, and I agree with the C's. So a lot of ways to think about this. The intuitive way was in C there. The C said the reaction, you have an intuitive feel for water boiling. Water boils at high temperature, and that seems to happen spontaneously. The gas is favored at high temperature. If you're very high temperature, you're not going to find liquid water. So the products are favored at high temperature. That's what delta G means. Products minus reactants. So the products have the low free energy at high temperature. At low temperature, you expect to find the reactants. So you expect at low temperature, delta G to be positive between reactants and products, and you'd find the reactants mainly. So that would say delta G low temperature positive, unfavorable. Delta G negative at high temperature, favorable. Absolutely. Another way to look at this is these two signs by looking at it again. A gas is produced from a liquid, so entropy increased. Boiling is endothermic. You have to put in energy to break those intermolecular bonds. Those intermolecular interactions are attractions. That's a potential energy that you have to overcome. You have to put energy in. So delta H is positive. And this should look familiar to you in a sense. If you know something about straight lines, this looks like y equals mx plus b. That looks like the equation of a straight line where X is the temperature, so the slope is delta S. The intercept is delta H. And you just know the signs. So delta H is positive, so the intercept is positive. The slope, delta S is positive, so the slope is going to be negative because that negative sign is there and T is always positive. So you can just sketch that out from the slope of a line as well. So this has a negative slope. That has a negative slope, but that has a positive intercept, and this has a negative intercept. So C is what we were looking at there. Sorry, I swiped too many times. Now I'm lost. Okay. We'll go by this one, and you can do that one on your own later, or we'll come back in review. So now we can do a thermodynamic analysis, a thermodynamic summary. We are now able to say that we can tabulate standard enthalpies of formation. We can calculate these absolute entropies, and these are not entropies of formation. They're the actual entropies going from 0 crystal up to the compound in whatever state. This would be probably 25 degrees C. That depends on temperature. But we can also calculate directly, since we know these two, essentially, we can calculate the free energies of formation. Again, we choose our own 0, so we choose the free energies of formation of these elements in their standard state, these elements in particular that I've shown here to be 0. And here's some other compounds. You can see some things that you would expect. We expect if you burn, you oxidize magnesium, you'd expect, well, that's probably spontaneous oxidation. We know it releases a tremendous amount of energy. They're both solids, so the entropy change doesn't matter very much. So that's a big free energy, highly favorable. There's some things that we expect to have. This is the one we just looked at, liquid going to gas. So we would expect to be able to subtract those two, products minus reactants. We take the products minus reactants, and we would have a standard state free energy difference that would say, in this case, well, we have to know the temperature. The free energy difference between those two at standard states, 1 atmosphere of liquid or 1 atmosphere of gas, pure liquid at 25 degrees C, is the expression we would find, or the free energy difference we would find there. So we just did that. We found that we looked at standard state at 25 degrees. Oh, we should have looked at that exact temperature. That would have been interesting. All we did in the Chem Quiz was we looked at the trend. We told you it was spontaneous at 25 degrees C, so we could have put 25 degrees C on that plot where it was negative. That would have been instructive to do. We'll come back and do that in review. Here are more of them. That's the same thing. So let's look at a couple chemical reactions now. This is where we're kind of bummed that we're not in Pimentel Live, because now we can do a bunch of chemical reactions and look at them. So let's look at a typical one. Here's potassium metal and water liquid reacting to form the potassium ions, the hydroxide ions, and hydrogen gas. This reaction is exothermic. It's a fun one. We get to watch it go exothermically. I think you would also guess delta S is positive because it produces a gas. So you would say that delta G is negative for all temperatures. You would say that's spontaneous no matter what temperature you go to. We can look at that chemical reaction. I think I have it. Reactions of alkali metals. These guys do not just potassium, they do sodium, all the alkali metals, sodium, lithium, potassium. They might even do rubidium, but they do a bunch of alkali metals. All those reactions are spontaneous at all temperatures, and they're all fun to watch. And these guys, they do it up. So let's watch what this. They even have a soundtrack. Why am I not getting the sound over here? So here's lithium. There it is, reacting with water. Exothermic, spontaneous, the little bit of lithium metal skitters around. Now, sodium will be more reactive. We're going to learn why that is soon. So there's sodium metal, dropping it in water. That reaction occurs, also exothermic, and it's proceeding rapidly and starts to explode. More exothermic. We're going to do it up. We're going to watch the explosion in slow-mo. That didn't look very slow-mo. Oh, there. Oh, love it. So now we're going to take a huge chunk of sodium and go to a lake and throw it in the lake. I'm not sure. I'm glad the Environmental Protection Agency didn't find them throwing sodium metal in a lake and watching the explosion of sodium metal. Just hydrogen gas released. So it's not crazy. Here's potassium. My goodness. Run away. Potassium, we're getting more energetic. Rubidium, now we're getting crazy. It's hard to even have solid rubidium. It's so reactive. Oh my goodness. The most reactive, huge chunk in water. Oh, give us that one in slow-mo. This is, I don't know how they got cesium. Oh my God, a tiny chunk just destroyed the beaker. There we are. Oh, I love these guys. Lonnie does this as well, but he doesn't do cesium and rubidium, and he doesn't do it. Francium is impossible. This is a lie. Yeah. You can't, francium isn't stable. You can't go get a piece of solid francium. But what do they want to do? Just give you an idea of what maybe solid francium might look like. A chunk of that in the ocean. Fantastic. That one's spontaneous at all temperatures. So let's look at another reaction. Here's H2O liquid and reacting with oxygen gas to form hydrogen peroxide. So in this case, this is an endothermic process, and the entropy change is negative. So delta G is positive at all temperatures. That's the bad combination. So this reaction is not spontaneous at any temperature, but we can watch the reverse reaction. We saw that. We saw Lonnie put a catalyst in this and going back that direction. That reaction is spontaneous at all temperatures, because going the other way is not spontaneous at all temperatures. So this reaction, as we know though, liquid hydrogen peroxide will just sit there on the bench, stable. So spontaneous doesn't mean that it can get over the activation barrier and form products. There still may be a high enough energy state between the products and reactants that prevents the reaction from going under normal conditions. But we know we can add a catalyst to that and make that reaction go. We've seen that one before. We've seen that one before. We'll go to a we make the reverse reaction go. Here's aluminum bromide solid making aluminum solid. So this is a decomposition. The aluminum bromide going to aluminum solid and bromine liquid. You would guess the formation of a liquid there is an increase in entropy. Delta S is positive. I'll tell you that that's endothermic. So this one, it matters. It's going to be spontaneous at low temperatures and not so spontaneous at high temperatures. So we're in that quadrant where we're in positive delta H and positive delta S quadrant. So we need a high temperature to make that go. That one we can see somewhere. Uh-oh, did I close the browser? Oh no, I'm just on the YouTube full screen. So peroxide, YouTube, alkali metals. Oh, I don't have aluminum bromide up here. Well, if I go to Lonnie, there's aluminum bromide. We can just watch that. Oh, bother. Stand by. So here's bromine liquid and aluminum metal. Bromine is a liquid, an element liquid at room temperature. So he just he's forming aluminum bromide. So this reaction is going in reverse of the reaction we wrote on the board. So it is, so we can show you the spontaneous part. All right, formation of aluminum bromide there. Come on, exit full screen, Chrome. Why can't I exit full screen here? I'm hitting the escape key. Sorry guys, stand by. We're gonna stop this. It's I shouldn't have entered full screen in Chrome. It's not letting me exit full screen. So this reaction we did in reverse because that's the spontaneous direction at room temperatures. This reaction here, magnesium solid with carbon dioxide solid going to magnesium oxide and carbon solid. We saw that, we talked about that briefly, the oxidation of magnesium. In this case, not the oxidation by oxygen itself, but by carbon dioxide. So this reaction, in this case, we're forming all solids. So it might be difficult to determine the entropy change, but I'll tell you in this direction, the entropy change is negative. Delta H, I'll tell you this is an exothermic reaction. So this one is going to be spontaneous at low temperatures. It's convenient in this case because solid carbon dioxide, as you know, does give you a low temperature. You can, it's used for refrigerant. You can buy it and put it in your cooler at the hardware store to keep things very cold. So let's watch that chemical reaction. If we can get Chrome to behave. Let's do it this way. Let's take this link and say play that link. Oh goodness, we have to watch an ad to see this one. Stand by. So magnesium and dry ice. So here's a chunk of dry ice, and they're lighting a little piece of magnesium. So the magnesium's burning now in the air, but another huge chunk of carbon dioxide, solid, we're going to put on top of that as the reaction proceeds. Now you would think that would extinguish any flame, because carbon dioxide is what you use to extinguish flames, but that just makes it freaking worse. And you get a beautiful, amazing chemical reaction of a crazy exothermic combustion, essentially reaction, an oxidation reaction happening in dry ice, in solid carbon dioxide. I love that reaction because it's kind of the yin and the yang of chemistry, the fire and ice together. That's cool. Just explosively spontaneous at low temperature. Fantastic. I just do not understand why I cannot go back to, I cannot exit full screen in Chrome right now. It's not, oh, I bet if I do this and then that, no. No, that is just the weirdest thing. We'll have to remember, don't go into full screen Chrome when we're doing these. So there's a bunch of reactions demonstrating the free energy changes and what reactions spontaneously proceed at different temperatures. So for what temperature range is this reaction spontaneous? We'll talk through this one together. We have the enthalpy change is around minus 200 kilojoules per mole. The entropy change, standard state entropy difference, is 200 joules per mole. And you can see now the magnitude difference, 1,000 times bigger enthalpy than entropy, because this is kilojoules, this is joules. So, but this one is per degree Kelvin. So if you get high temperatures, this will have a bigger effect. But you can say for what temperature change is the reaction spontaneous, and you can see the factor of 1,000 between those. So delta H is tending to make it spontaneous because it is negative. Delta S is working against you. That's entropy decreasing. So you have minus T delta S. That makes that term positive. So what you have to say is, well, that positive term has to be smaller than this negative term. And they are different by a factor of 1,000. So if you go to temperature ranges above 1,000, then minus T delta S is a big number. You have to stay at temperatures below 1,000 for the enthalpic term to be bigger than the entropic term. So here are those explanations, and we understand that T delta S and delta H are around the same. T times the entropy and delta H are around the same at 1,000 K. So temperatures greater than 1,000 K, temperature greater than 1,000 K, delta H is positive. That's not, or delta G is positive. That's not a spontaneous condition. I have to go to low temperatures below 1,000. And again, here low is relative. 1,000 Kelvin is where the cutoff is, where it goes from free energy positive to free energy negative. Okay, let's work through an example here. Plot the standard state free energy change versus temperature for the atomization of hydrogen gas. So we're going to go from hydrogen in its standard state, H2 gas, to atoms of hydrogen. We can write that down. Here it is, hydrogen gas going to hydrogen atoms. Molecules going to atoms. So can we predict without going to a table, delta H and delta S for these reactions? I think we can. Why is that? This is just breaking the hydrogen-hydrogen bond and making the atoms. It always takes energy to break a bond. If you take nothing else home from Chem 1A, you have to put energy into break bonds. That means when you form bonds, energy is always released. So that energy that's released when you burn something is because carbon dioxide CO bonds and water HO bonds are being formed. And that energy release is greater than the breaking of your hydrocarbon bonds. So we can say by inspection, just by looking at this, only bonds are being broken. So that means I have to put energy in. That's endothermic. So if I'm going to plot this, the intercept of the delta G versus T is positive. I make twice as many particles, so twice as many microstates. Delta S is positive, an increase in entropy. That means the slope is negative. Delta S is positive, but it's minus T delta S, and T is always positive. So minus T delta S is negative. So I can plot that in a straightforward way. Standard state free energy difference. The intercept, we haven't drawn the intercept, but it's up here. That's the intercept. That's delta H. The slope is negative. So I can sketch out that plot. Oh, goodness. What is delta G standard for the combustion of glucose? In what temperature range is the reaction spontaneous? So this is a chemical reaction important for biological systems. This is glucose, sugar, being oxidized with oxygen, something you breathe in, forming carbon dioxide and water, something you breathe out. So this is a biological metabolic reaction. And I will tell you, I mentioned this in the first day of class, the way this happens in your body is absolutely gorgeously fantastic. And it's not burning. There's not a little combustion chamber in your stomach that makes this go. It's a beautiful electrochemical, mechanical thermodynamic reaction. So we can do this one by looking at a table. So we'll get the standard free energy of formation of the sugar, glucose. Oxygen's an element in its standard state. Look up the standard free energy of formation of water liquid and make sure you get the liquid, because there's also gaseous water or solid water, and the standard free energy of formation of carbon dioxide gas. And then we can do our thermodynamic cycle, the standard state free energy difference between these products and these reactants. I can just do the math. 6 water molecules and 6 carbon dioxide molecules are the products, minus 1 glucose and 6 oxygens. And again, oxygen element in its standard state, we're going to enter 0. So minus 2,876 kilojoules per mole. Awesome. And this is the useful work. That's not just the enthalpy. This is the tremendous amount of useful work we can get out of that. And we use that useful work to do to run our muscles and stuff. It's cool how it's stored. We'll talk a little bit about how much you kind of lose in the biological process. Your body stores this energy as ATP, adenosine triphosphate. And so I got to get it to ATP, and then I have to use the ATP later in your body. So we'll look at that cycle too, because it's fun. And I know many of you are biological scientists or going into medicine, so I try to slant this in that direction. So let's plot it now. Delta G is delta H minus T delta S. I calculated that standard state free energy variable. That is standard state, so around room temperature. It's spontaneous. What about all temperatures? Well, the standard state enthalpy, we can intuit, we can guess. Remember, I told you if you take nothing else home from Chem 1, hydrocarbon burning in oxygen makes carbon dioxide and water exothermically. That's burning. That's a flame. So delta H is negative. There's a release of enthalpy. Delta S we can clearly see is positive. We go from a solid to a liquid and a gas. So a solid and a gas going to a liquid and a gas. Many more moles, just plain more particles over here. Overwhelming entropic combination, and that's awesome. Use intuition or a calculation to get delta H. Delta S must be positive because the reaction is spontaneous, at least at the temperature. So delta H standard room temperature, we found that to be negative. We're looking at the other temperatures, but we know it's spontaneous at all temperatures because delta H is the intercept, and that's negative. The slope, delta S is positive. T is always positive, so that minus sign makes the slope negative. That's never going to be not spontaneous. Awesome. We can always, whatever temperature we operate at, we can get useful work out of that reaction. Yay, let's keep going. Oh, that's the thing we have. So summarize just a bit. So we have this idea that the entropy change of the universe is always positive for any spontaneous process. That's always positive. But it's hard to that's my delta symbol. And I love you guys. So delta S is universe always positive for any reaction that occurs. So the universe always increases in entropy. That also, we talked about last time how that gives us the idea of the arrow of time. What will happen in the future if you have two situations? The one that's happening in the future is the greater entropy of the universe situation. And we said the entropy of the universe is always increasing. The Big Bang, you had all the mass in one single state, all the mass of the entire universe. Well, that's the hypothesis. In a single state, in a singularity, we say that expands dramatically, the Big Bang, space itself expanding. So you get plain more space, you have more microstates, and everything blowing apart makes entropy increase continually as the age of the universe. And we can plot that and we can say that's the direction of time. It goes in that direction. Actually, speaking of time, this is funny. This is my personal computer, so I can show you. I can show you this. I was up at the ranch this past weekend, and we put these are our blueberries, and the birds eat the blueberries, so we cover them with netting. And I set the iPhone up on time lapse just for fun. So here, let's watch the direction of time in the hoopting the blueberries, the netting of the blueberries, done on the iPhone. Is iPhone a sponsor? We don't have sponsors. I keep doing these ads. for nothing. So there we bring out the nets and we pull them over those hoopties and tie them up. No birds can get in, and we get the blueberries to ourselves. As me and my partner up with our funny hats at the ranch. So direction of time is what we get. Oh, as long as we're there. So last time we were here, can I show you that? Oh, that's not obvious. Okay, never mind. So we have this idea of the direction of time. Now we're going to look at that case in free energy where, actually, let's do this. I can't believe I have to do this every time. How do I reset to the whiteboard to go to a fresh one? I'll have to look at the manual. So we've been plotting this whole standard free energy versus temperature. And we said, well, when delta G is negative, that's spontaneous. When delta G is positive, that's not spontaneous. And all spontaneous means, it doesn't mean the reaction goes fast or it's going to happen without energy involved. We saw that hydrogen peroxide sits there on the desk. It spontaneously goes to water and hydrogen gas, but spontaneously just means that's favored by the universe, that the products are lower in free energy than the reactants, but it doesn't tell you anything about how it's going to get from one state to the other. You can imagine a state where the free energy difference between the products and reactants is 0. There's a temperature here where the free energy difference between the products and the reactants in their standard state is 0. And you would say, well, then the universe is indifferent to whether I'm in the products or reactant state. So neither is favored by the universe. Either is equal. They're equally likely, the products and reactants. So that's the situation we're going to look at now. And that, you might already be guessing, is called equilibrium. So let's talk about equilibrium. So far we've talked about static reactions, and we're going to continue to be the static case. In every discussion of thermodynamics, you're talking about the equilibrium situation. Remember, time is not a thermodynamic variable. So if I look at the free energy difference between two things, or I look at the enthalpic reaction, what I'm talking about is the reaction at equilibrium. What's the difference between those two things? Standard states, I have a special case. I have everybody 1 atmosphere and 1 molar. But if I'm talking about the free energy difference of a reaction, a real reaction, or the enthalpy difference between a real reaction, that's the reaction at equilibrium, essentially after infinite time. So we know reactions don't start out at equilibrium. So here's a chemical reaction, A and B going to C and D. We define this thing called the reaction quotient. I'm shouting. I get so excited. I'm getting hoarse. We have a long semester here. I'm going to try to sound enthusiastic, but not shout. So we define this thing called the reaction quotient. It is a quotient. It's a numerator and a denominator. In the reaction quotient, we put the products, and in the denominator, we put the reactants in a special way. We take their concentrations, and remember I put so this is for reactions in solution. These brackets mean the concentration in moles per liter of the compound C, the concentration in moles per liter of the compound D. And then in this quotient, we do this special thing where we raise those concentrations to the stoichiometric coefficient, the power of the stoichiometric coefficient. So it's the number of moles of C to the stoichiometric coefficient C power. That might seem arbitrary, but it's just a definition for us. We're just going to say, we're going to define this thing called the reaction quotient. It's going to look like that. It turns out, I wish I had time to derive it for you. It's a beautiful, this occurs naturally if you look at the entropy changes, the microstate changes, how changes in concentration affect the overall entropy of the system. This is what you get. And you can kind of see it because you'd have, remember, entropy is natural log of the ways, and it turns out that's related to the natural log of the concentration. So you'd have natural logs of products and amounts of them, and natural log of reactants. And you know, if you have a difference in natural logs, that becomes a quotient. So that's just a brief idea of how this thing seems arbitrary to us, but you can derive it. It comes from the free energy changes, the entropy difference between the products and reactants. So with that in mind, we have products and reactants. If we start out, though, with reactants, which we often do, the reactants will decrease as they form products. The concentration decreases of A as the reaction proceeds. Now I'm starting out with all reactants and not any products, not the standard state. This is what you do in the lab. If I were in the standard state, what would the concentrations of everything be? Shout it out. 1. Standard state is all concentrations are 1. So Q is 1 in the standard state. Boring. Okay? I keep saying this over and over because no matter how many times I say it, people don't know what the standard state is. It's arbitrary, it's crazy, but every concentration is 1. Every partial pressure is 1. And that is how we compare things. This is not the standard state. I'm starting out with A and B and no C and D. But they're going to make C and D. Start out with no C and no D, but those concentrations would increase over time. But here's the thing. After enough time, the concentrations stop changing. This is typical of chemical reactions. And when the concentrations stop changing, what happens to Q? Well, initially Q is kind of interesting. When I started out with all the reactants and no products, I had 0 here and a number here. So that's defined as 0. And then the reaction proceeds, C and D increase, so Q is changing through this whole process. But it'll get to a point where it stops changing. The concentrations stop changing. Q then stops changing. And you can measure the concentrations at that point, and you can get what that static value of Q is. The concentrations don't change. That's what we call equilibrium. Now, that doesn't mean the reaction stopped. It could mean the reaction is going very slowly, but it also could mean the reaction forward and reverse are going at the same rate. So whenever you use up a little A and B to make C and D, somewhere else in the reaction, some C and D go backwards and form A and B. That would keep their concentrations constant. So just because they're constant doesn't mean everything has stopped. It's a dynamic equilibrium. So when that thing Q stops changing, it has a constant value. We call it K now. So we differentiate between reaction going and reaction at equilibrium. The going value of the quotient is Q. The equilibrium value of the quotient, we give the symbol K. And it's an interesting, cool fact of nature that regardless of how you start out, No matter how much A and B and C and D are present initially, the concentrations always arrange themselves. So they could be any bunch of different numbers, but they always come to the same value of K if you're at the same temperature. It's a crazy property of the universe that those combinations work out. That means you can tabulate these. You can, for every reaction, you can calculate a K, and you know it will get that way from any starting conditions. Very useful number to know. So we've already said in this part, Q is changing and it's less than K because you have lots of reactants. The denominator is big and the numerator is small. That means the reaction is going to go towards products. You know, eventually Q has to equal K. So if Q is small, the denominator is too big. So you're going to go towards products. So this is now telling us something about the dynamics of the situation, where I'm going to go. So if I know where I'm going to go, we'll foreshadow. There's another thing that tells us where I'm going to go. The free energy difference between the products and reactants. So this relationship, Q versus K, has something to do with the free energy difference between the products and the reactants in real time at that moment, not the standard states, the reaction free energy, not the standard state free energy. When Q equals K, that's the state we call equilibrium. But it can happen from either direction. We said you can put anything you want in the beaker to start with, so you could put more C and D than A and B, and Q could be bigger than K. But all that tells you, well, I'm going to go back towards reactants till Q gets back to K again. So we have this QK situation. K is just a number. Q varies depending on what the concentrations are, but the quotient always tends towards that constant K, regardless of where you start. So here's our dynamic equilibrium. It's once we're at equilibrium, the reaction's going back and forward at the same rate. So it's not a static case. The macroscopic concentrations aren't changing. We measure a concentration and we can't tell the reaction's going because the concentrations aren't changing. Q is a constant. So here's a beaker with some moles of X in it. And we can look at, let's say that this acid, HAC, acidic acid, is X in concentration. If we start with that, that reacts to form H3O plus and AC minus. This AC isn't a compound, that's an abbreviation for acetate. So that's not particularly important, but you could take the concentration of the acetate, the concentration of the H3O plus over the concentration of the HAC in water, and you could write the equilibrium expression. This is the expression for Q. You could look up the value of K because it will eventually come to equilibrium. Interesting thing here, the water liquid doesn't appear in equilibrium expressions. In fact, pure liquids and pure solids do not appear in our equilibrium expressions. That's something you just have to know. You might be able to intuit it because if those were to be present, they're present on either side and the entropy of those little things don't change. But that doesn't matter. All we need to know is pure solids and liquids don't appear in our expressions for a Q. So that's an aqueous solution. We could have a heterogeneous solution where you have a solid, silver chloride, in equilibrium with the dissolved ions, silver ions and chlorine ions. That's a possibility. That's dissolving salt. You put sodium chloride in water, you get sodium ions and chlorine ions. The water tastes salty. Silver chloride the same way, although not very much dissolves. Silver chloride is not as soluble as sodium chloride. In this case, you would write the equilibrium constant, or the equilibrium expression, Q, the expression for Q. It eventually becomes a constant, but the expression, the quotient is silver ion concentrations, chlorine ion concentrations, and you would think, well, over the reactants, but pure solids and liquids do not appear in equilibrium expressions. So in this case, the equilibrium quotient is actually just a product because the pure solid on the other side doesn't appear. You could do gas phase reactions, and when the reactions are in the gas phase, we use the pressures of the gases rather than the concentrations. So this reaction that we looked at before, the pressure of just the NO2, the pressure of just the N2O4, when you talk about individual gases in a mixture, they each have a partial pressure. So the pressure that comes from the NO2, the pressure that comes from the N2O4, the partial pressures we would write down. So we would take the pressure of the N2O gas by itself, the pressure of the NO2 gas by itself, and we would write that quotient, and that would come to a constant value, equilibrium value. We could do a phase change. We've done this a lot. We've looked at water and gas in equilibrium. And when the water and gas are at equilibrium, then it's a gas. So pure solids and liquids don't appear, but pure gases appear as their partial pressure. So it's the pressure of gaseous water over liquid water, which is the expression here, that comes to equilibrium at any given temperature. So the pressure of gaseous water, the partial pressure of gaseous water over any body of liquid water is a constant. It comes to equilibrium. When water molecules evaporate, you have gaseous water molecules, but in equilibrium, for every evaporation step, there's a condensation step. So the pressure, the amount of water gas molecules stays the same. So pressure in a gas is directly proportional to the number of particles. Pressure comes from the particles banging against if you have in a balloon, the pressure comes from the particles banging against the sides. They're moving around, they're banging into the sides. In a balloon, the more particles, the more banging, the higher pressure. So we'll remember in this case, pressures are very similar to concentrations in that moles per liter. You could also write the pressure as moles per liter here. If you had a liter volume of a liter volume balloon with a number of moles of gas in it. The more moles, the more pressure in this case. The more moles here, the higher the concentration. So they go the same way. Now, when you start to look in textbooks, these equilibrium constants, for some reason, it bugs me. They give them little designations. They call this a Ka, an acid dissociation constant. It's just an equilibrium constant, nothing special about it. It just happens to refer to an acid-base situation. We call these KSPs if it's a heterogeneous dissolving. That stands for the solubility product, and it is just a product. But it's still just a K. It's still just a equilibrium constant. It's still just a Q. Nothing special, just a name. This is Kp, the pressures of the system, and this one is the vapor pressure of the system, actually. So that one's kind of interesting. The pressure of the pure gas over the pure liquid is called the vapor pressure. So there we define it. Vapor pressure of water is the pressure of the gas phase above the liquid phase, regardless of the temperature. And we know liquid, when you have liquid water, there is some gaseous water above it. There's some vapor. So this is an equilibrium but we know it's favored at higher temperatures. The gas is favored, the liquid is favored at lower temperatures. We saw that free energy plot. And again, we see the size of K, the size of the equilibrium constant, is going to depend on this free energy difference somehow. Because when the free energy difference is great, when this is very negative, then you have products favored, and K's will be large. When delta G is negative, K's are going to be small because the reactants are favored. The denominator is favored in our expressions. I'm going to draw something called a phase diagram. We don't need to know too much about this, but if you look at all the pressures and temperatures of this gas, you can say, well, at some pressures and temperatures, high pressures, low temperatures, so if you squeeze it and you freeze it, you'd expect it to become a solid. So phase diagram, the regions of pressure and temperature space, so another space, we keep looking at these different spaces, these coordinate systems, pressure and temperature space, high pressures, low temperatures, you'd expect to see the solid. Intermediate, you'd expect to see the liquid. And at high temperatures, low pressures, you'd expect to see the gas. The reason I draw it is these lines separating the phases are where the phases are in equilibrium. So every pressure and temperature along that line represents a place where the solid and liquid are in equilibrium. Every point along this line represents this equilibrium, where the liquid and the gas are in equilibrium. And the liquid and the gas can be in equilibrium at 25 degrees C. You don't have to go to boiling 100 degrees C. That's another situation where the liquid and the gas are in equilibrium. But then the equilibrium pressure of the gas is 1 atmosphere. You can be in equilibrium at 25 degrees C, but the equilibrium pressure of the gas is just smaller. So we can write Q, and Q is the pressure of the water gas, and we're calling it the vapor pressure. And it is a function of temperature. When you're boiling, that vapor pressure is 1 atmosphere. At room temperature, it's much lower. It's 3/100ths of an atmosphere. You could read it off the curve. You could say, well, let's go to this point on the curve. That, let's say, is 25 degrees C. And the vapor and the liquid are in equilibrium there, everywhere, every point on that line. That means if that's 25 degrees C, then 100 degrees C must be higher than that. That's obvious. If you go to 100 degrees C, you would get to a higher vapor pressure. And we already know that. The vapor pressure of the gas at the boiling point is 1 atmosphere. It's lower at room temperature. In fact, the value is 3/100ths of an atmosphere, so not very much. But it is in equilibrium. So K for this reaction at 25 degrees C is 0.3 atmospheres. That's the unit of pressure. If I go the other direction, gas going to liquid, so obviously Q's matter what the products and reactants are. If you just reverse a reaction, you invert Q, of course, because there's products over reactants. So you just take the inverse in that case. So that tells us that you can talk about the equilibrium going from products to reactants, reactants to products. It's still constant. We can write 1 over 0.3 and get 300 if we want. We're not going to do that, but it's a different numerical value because we wrote the reaction in the other direction. Okay. we don't have time to talk about this, so we'll start here next time and talk about the relationship between Q's and K's for a couple reactions. Are there any questions coming from the chat or anything? Good. I'm amazed there are so few questions coming from the chat. Well, or maybe I'm gratified. Maybe the explanation is so beautifully perfect that there's no confusion whatsoever. Or maybe it's so obtuse that you can't even formulate a question. Either one, we'll see you tomorrow.